McMaster here in my Silicon Valley garage.
Hi, and I'm Yusuf, and we got a great episode for you today. So, John, can you tell us what we're going to be covering today?
Sure, as you may be aware, a lot of the stuff I do with my microscopes is recovering firmware from microscope images. And I get a lot of people asking, John, what is that process about? And you may be aware there are multiple stages of that process. I think you took a look at a slide deck that I had a bit back, right?
Yeah, the capturing mask ROMs.
Sure, do you have that up, or maybe I can bring it up on my screen over here?
If
Let
you have
me,
it handy, I have it handy too.
sure, let me do this here. Okay, can you see my desktop here?
Yes, I can.
Great. So normally what you do is you start by actually photographing a mask ROM using a microscope, and you'll get a JPEG, something like the one on the left. And for our example, I have this Game Boy here. Have you ever used a Game Boy? Is that something
Oh,
you kind
for
of grew?
sure.
You
For
sure?
sure.
Favorite games or anything like that?
Tetris, man. Tetris all the way.
Tetris. Okay, cool. Well, what you may or may not know is that when your Tetris code started running, this was actually the very first code that it starts with. This is the so-called boot ROM for the Game Boy. Do you know what a boot ROM is?
That's the absolute initial code that runs when a machine starts up, right?
That's right. And so if we want to start getting that code out, we can take a photograph of it like this. But how does this actually turn into useful firmware?
How does it? So, and what do you mean by useful firmware?
Well, if we want to actually analyze it, like disassemble it or something of that sort, we actually have to do this first step where we take photographs, and then we have to somehow kind of get a high level abstraction of, the ones and the zeros that are here. And from there, though, even if you have this high level abstraction, you need to somehow turn this physical, 2D array of bits into an actual firmware file. And that can be a little bit difficult to do. Like, is it intuitive, like where bytes are in this image here?
Like, it looks like an array. I would think, starting at the left and moving right, top down, I guess. Is it 8 bits top down?
Well, that's my point. I think it's pretty non-intuitive, like how you do this translation. Like where is the least significant bit? Where's the most significant bit? Where's the highest address? Where's the lowest address? So what I was thinking today is there's a lot of write-ups on how to convert, these like into this 2D array. But there's not a lot of information on how to do that second step where you take this 2D array and convert that into firmware. And that was what I was thinking we would talk about today, is this step over here, where we convert that into usable firmware.
Sure. So I guess for the first part, we're going to take the turkey out of the oven, like in a cooking show, and just say
Yes,
we have that data, right? So we're going to start with the text file with the ones and zeros that we have captured from the image.
that's right. And you can do multiple ways to get this, converted. Obviously, I can, just type this out by hand. Like if I look, maybe I'm going to call the dark spots a 0. I could say, this is 0, 0, 0, 1, 0, 1, 0, 0, and so on, and just type that out. Fortunately, someone has done that work for us already. So if we go to this website here, and I have a link to this in the video, there's actually, well, I guess there's a few files here. Let's go with this one. Someone has already typed these out for us. And this isn't quite in the same orientation as the microscope image. I think it's been rotated 90 degrees. But if you look here, for example, here's the 0, 0, 0, 1, 0, 1, 0, 0. That corresponds, maybe I can get these both on the screen at the same time, just so this is really clear. This is rotated 90 degrees, but you see this is the top right here, corresponds to what's there. Like you see this 1, 1 here, for example, corresponds to
Yep.
that 1, 1 there. Does it make sense?
Yep. Makes sense.
Okay, great. So now we started talking about how do we convert this into some sort of firmware. Do you have any sort of ideas about how you might go about that?
So, I mean, if we're lucky, you just dump those ones and zeros in sequence as bytes into a file and you got firmware. But I expect that that's not the case.
No, and let me also check, see if there's any questions so far. Just make sure I'll check that occasionally. No, because the way that they usually set up these chips, and let's zoom out a bit, a lot of times there's some sort of interleaving. For example, you might naively think that this is going to be a byte right here, because there's 1, 2, 3, 4, 5, 6, 7, 8. You might naively think, oh, this is the first byte right here, and then here's the next byte here. But when they're physically designing these chips, the way that they want to mux the bits out, if we look at, gosh, I think there's something like 16 or something like that of these groups across, what you might actually find out is that this is like one of the bits here, this whole group, and they're kind of funneling these down as you go down into one output bit here. So like maybe this is an address bus over here, and maybe this is maybe this is the data bus coming out over here. So it can be a little bit non-intuitive to know exactly whether all the bytes are grouped together or whether all the bits are grouped together. And you might have to do a little sleuthing work to kind of piece that all together. Does that make sense? So far, there could be a few different schemes.
It does. So here's a question for you. Can you figure out the arrangement from the circuitry there? Is it something that's easy to do, or are there other ways you try before that?
Oh yeah, you definitely can do that. So I'm not that familiar with this ROM. I haven't looked at this in detail, but if I had to make a quick guess based on what I'm seeing here, this looks to me like it's probably a NOR metal programmed ROM. So let's break that down a bit. So these metal linkages right here is the white shiny, it's probably aluminum. And you can see that sometimes there's a metal linkage here and sometimes not, right? In fact, maybe what I could even do, I'm gonna go to, there are some diagrams from Sergey. Let's see if I could bring that up real quickly by chance that I think are linked on this page. Okay, this may help. This is NOR, yeah. So this is roughly, I think, what we've got there. And the basic idea is you have these, in this case, I think they are pull-up resistors here, and you have these bit lines going up and down here. And the idea is that normally this bit line is at like, say, VCC, say a 1. But if you have a transistor here and you turn it on, you're going to pull that down to a 0, right? Does that make sense so far? Just a basic sort of, drain the power way. And you can imagine now the so-called word line. Let's talk about word line 2 here, for example. If sometimes you have these transistors here and sometimes not, as you start to actually apply, the control gate voltages here, whether there's a transistor or not, this one's going to bring it down to a 0 here, but there's no transistor here. So this is going to remain a 1, right?
Yeah.
If we attach all these in parallel, similarly, if we apply power here, these two transistors are going to turn on, which is going to drive, these lines down to 0, but these are going to remain 1s. So in that case, you actually get 1, 0, 0, 1 out of these bit lines, when you activate word line 1. So this is a schematic representation of what I think we have over there. So let's now go back and look to see how maybe that's realized on the real chip. So I think what we're seeing here is instead of having transistors either present or not, like was in that example, I think what we may have is the transistors' outputs are maybe being connected or not, or something of that sort. So let's take a look of what this might be. The first thing that sticks out to me is I think, because I see these contacts here, I think there's some sort of power distribution happening here. Maybe what we're seeing, for example, is these could be ground connections or something like that. And they might always have the transistors present. But you can imagine if we go back to this, if this ground connection was actually programmable, it's roughly equivalent to either placing a transistor or not, right? Because even if this transistor's control gate is put on, so that is we have this bit of circuitry, if there's no leakage here, connection here, which is going to drain this pulled up line to a 0, it's almost as if the transistor wasn't there. Does that make sense?
Mm-hmm.
Okay, so I think that's what we've got going on here, is the transistors are present everywhere. And if we activate that transistor and there's a metal leakage to pull that line low, it's going to drive it to a 0. Otherwise, it's going to get a 1 or something of that sort. The bit polarity is a little bit nebulous because you can invert the polarity any part of the way. I'm just going to assume these are 0s right now and these are 1s, but we're going to have to sort that out a little bit later. Okay, so with that in mind, I'm going to suppose then, let's think this through a bit. If these are the linkages here, I'm trying to think if there's an inherent transistor orientation. So these are, I'm going to suppose, I'm going to guess that maybe these are some of the word lines going across here. just based on how this would normally be laid out in a NOR implant ROM, but I don't know if that's necessarily the case. And if that was the case, what it would mean is that you would activate one of these rows at a time to get some of your data. But here's the problem. You can see that if we activate one of these rows, there's actually quite a few number of bits across this whole row, right?
Yep.
Okay, so we need to somehow smash that down to 8 usable bits, assuming this is an 8-bit CPU, which glossing over a little bit, because I know this already got some angry, I shouldn't say angry, some comments on Twitter. This is roughly speaking sort of kind of a Z80. It's actually a derivative of a Z80 called a LR something something. I think you maybe have the example there. Do you have that name handy?
Yes, it is the
Some more questions.
LR35902.
If I can actually, does it let me speak here? Okay, I'll just say hi. You probably hear me on the video, but there's a Furtech there. Furtech, sorry, not Furtech. Sneako May. Anyways, yeah. So we have to break this way down. The most common way that I would say that I see this is you have, let's say this was a smaller ROM. Just hypothetically speaking, I'm going to zoom this in. So we just have these 4, 1, 2, 3, 4. Well, okay, let's cut this one off. So let's pretend that we just had this and we had 4-bit words. The most common thing that I see is you'll scan like from left to right or right to left within these groups, and they'll have an additional selection circuitry over here that will do some final muxing. So that is, what you'll do is you'll activate this entire row here. All of these lines will have bits, but then there's another sort of mux down here, which is maybe this right here, which will select one of n of the signals here. And that way, you kind of do the first level selection here to activate a row, and then you'll start selecting some of the columns, and then that will filter down to, final bits down here. Does that roughly conceptually make sense?
Yes.
Okay. And that's roughly what I would expect to see here, is something of that sort. It also could go the other way. I might have this backwards. Maybe these are all, word lines going all the way across here, and the bits come out here. We would need to do a little bit of sleuthing to maybe figure out the final orientation. But since there are relatively few ways that these are typically laid out, with a few guesses, we usually can figure it out pretty quick. Does that make sense so far?
Yep, makes sense.
Okay. One of the ways that I like to do this is I will learn a little bit about the architecture, and I will try to figure out what is a good starting instruction. An example I like to give is that for 8051 assembly, typically there's a jump table at the start of the chip. And almost entirely, always, the reset vector at address 0, which is a good place to start, is going to have a jump instruction, which is either 02 or 01 in 8051 assembly. Now, I would use that then to say, oh, the very first nibble, that is the 4 bits of an 8051, are almost always 0. And then I would start going on here and I would say, okay, let's say this was a 4-bit CPU, hypothetically, maybe not really. I would say, oh, maybe this is the very first bit over here. So I'd say, okay, there's a 0 here, 0 here, 0 here. And let's pretend this was a 0 here, but it's actually a 1 here. I would say, oh, the first nibble is all zeros here. If I shift it to the left, hey, maybe that is the start of it. And then maybe if I look to the right, I would say 0, 1, oh, that's not a 0 there. It's probably not that orientation. Similarly, look at the corners here. Maybe that works out a little bit cleaner. And just keep running through some permutations like that to get a touchy-feely idea. In our case, though, we don't have an 8051. Do you remember what do we have instead?
LR3902.
Yeah, so I've cheated a little bit. So just to talk about how we're going to cheat a little bit today, this ROM is already well known, and that's part of the reason why we're using this as a test. And I'm not that familiar with Z80-like assembly, but at least for this one chip, I happen to know from looking ahead that the very first instruction is to basically initialize the stack pointer, which does in fact have a lot of zeros on it. So what I'm going to do is I'm going to get a little snippet here, and I'm using a tool called UniDasm. I don't know if that's pronounced right. Do you know what this tool is by chance?
No.
This is a tool that comes with MAME. So this is a kind of an arcade emulation-ish platform. And the important thing is, I don't know if there's like a list arc or something like that. Here we go. I really like this tool because it is a disassembler that just supports a number of very odd and obscure architectures, versus GCC, which is relatively limited. It has x86, maybe ARM and a few others like MIPS, but it doesn't have this sheer architecture support, especially for these embedded architectures like this tool does. So anytime I need something more embedded, this is kind of my go-to. Anyways, so if I go to this now, and we're just going to look ahead a little bit because we happen to have this binary. We're just going to learn a little bit about its mapping. I'm just going to do head 1, and we can see that this happens to be the first instruction, okay? So cheating a bit, but I would say that it's not unreasonable because oftentimes I could see that other Z80 might have this as their first instruction. So just kind of use your knowledge of what you might know. Okay, so with that in mind, we kind of want the first byte to be hex 31. So let's start by typing that out as, maybe I'll just put a new one here. So we have OX31. What is that in binary? Are you able to, by chance, decode that?
Something, something, something. Going this way, it's 1,
well, okay,
0, 0.
let's cheat. Okay, so we'll cheat a bit. So I'll just do. So if you're not very good doing these conversions, if you do something like Python, there's this bin function, and this will decode it for you. So that's one way to do it. Actually, I'm going to remove this 0b so it lines up. But just for reference, if you get stuck, this is a good way to do it. Okay.
Or you can even Google it.
Yeah, I'm sure you could, or Bing it. Trying to get that to catch on. Okay, anyways, so let's take this as an idea that I think that there's going to be some sort of interleaving, like I mentioned. Assuming my theory is correct, that these are the bits kind of grouped like this, I would suspect that the most common things that I would see are either that these two blocks are aggregated together to form a bit, or what you do is you get 1, 2, 3, 4, 5, 6, 7, 8, and then it skips over. So one of the let's say the least significant bits is here, and some of the least significant bit is here. And I've seen that done that way a few times on different chips. I'm not exactly sure why that's common, as it seems to me a little hard to make the decoders that way, but alas, I have seen that a few times. So with that theory then, let's start by looking at the corners, kind of here or here, and see if we can by chance start seeing that pattern here. So let's see if I can get these both on here. And so what I'm supposing is, like, if we look in the upper left-hand corner as we skip along, maybe we'll see this pattern. So I'm going to go 0. So we've got a 0 right here. And we could look at, a text file or something. It doesn't have to be in here. But you can see, okay, there's 0 here, there's a 0 here, and there's a 0 here. And you see that doesn't match this, right? Because this was, we wanted 0, 0, 1.
Right.
So that's probably not it. Okay, let's try maybe the other corner here. So we have 0, 1. Okay, that doesn't match this. And I should also emphasize, I'm mostly looking for the polarities, that kind of entropy pattern matches, because we don't know if this convention for 0 and 1 is correct. Just focus on the transitions more than the actual bits. Okay, let's look down here maybe. So it's a little bit harder to see the divides, but I think this is 0, 0, 0. Okay, so that does not match. We can try to go to the other. Oh, we also might not have the most significant, least significant, correct? So we should also maybe flip this to look at this side first. Let's see if we do 1, 0, 0. No, that doesn't match this way. Let's check this corner. So we have 0, 1. Okay, so if we had the opposite polarity, this could be correct. So assume this was a 1 and this one was a 0. If we've switched that could potentially be correct. Except
but
it
this
falls.
One isn't.
Yeah, that one's not. Okay, so let's flip this down here now. What do we have? So we have 0, 0. So that violates that right there. And what's our other corner here? So we have 0, 0, Maybe we should switch to the other view. I'm getting lost in all these bits right here. So we have 0, 0, 0. Okay, and that doesn't really match anything on either side of this. I would suggest then, as the next step, let's go to the corner over here. And why don't you, can you follow my example and see if you can sound out?
Let's do that. So
Sure.
let's say we got a 1, 0, 0, which kind of could be, yeah.
That could be that. Okay, wait, let's keep going then, because that's promising. So 1, 0, 0. And then what's next?
Okay. 1, 0, 0, 1. So that's not what we want.
No, wait, that is right, isn't it? It's because I'm going to type this out, the corners. So you're looking at the upper right-hand corner, right?
Yep. 1.
Okay. So we've
actually,
got
if you zoom out just a little bit and leave the image there, I think it's easier to work with. Yep.
Sure. So it's
1, 0, 0, and then there's a 1.
Right, but that
no, we need 3.
I see. You're right. Mm-hmm. You're right. Yeah, I'm miscounting. Okay.
So let's do the bottom corner now. So it's 0, 0.
But we should also do this one though, right?
Oh yeah, yes. So let's do that. 1, 1, 0, 1.
1, 1. No, it's 1, 1, 1, isn't it? Because it's 1, 1, 1.
1, 1, 1. Yes, 1, 1, 1, 0. That also doesn't match up. Yeah.
Okay. So let's check down here now.
0, 0, 0. That doesn't match up.
Nope.
Let's do the other corner. Is that a 1?
Yeah, it's a 1.
1, 1, 0.
Wait, so it's 1, 1. And then it's a little hard to track, isn't it?
Yeah.
So it's to scan. So 1. I'm getting confused myself here. Wait, sorry. That is wait. This first one is a 0, isn't it? Because it's this is the separator right here.
Right.
So that's actually a 0. Yeah. Sorry, so that's a 0, and then that's a 0.
0, 0.
Okay, so it sounds like we didn't get. Okay, so that's unfortunate. So that's usually what the easiest is, something like that. One of the things that I also mentioned is that it sometimes can skip. Like maybe you would have a little bit of, oops, if I could zoom out. You might have some of the least significant bit here, for example, and some of the least significant bit here. But at this point, I think we're going to cheat a little bit, if that's okay with you, just to kind of speed things up a little bit.
Real quick, right? So we did horizontally, we went and we scanned through. How about vertically? Would that be something you would do here, or is there a reason you're not looking like vertically?
We definitely could. The main reason why I wasn't doing that was in the interest of time.
Okay, but generally you would. Generally
you would. And this goes back to cheating, is we did do some preliminary research. We didn't actually try decoding it like we did like this. But I did get some high level information just to make sure we could get some progress on here. And what that high level information was, and I don't know if I have those results handy, I probably should have had them, is I mentioned that we happen to have the binary from, just happens to be out there. So to accelerate this project, I did some frequency analysis of the bits in that binary, and I compared them to the bits that we found on the site over here, wherever that is. Did I close that? File. Yeah, I don't know, maybe I closed it. But anyways, I can bring it back up though.
And I think that image right there actually shows you the order.
Oh, which one?
The one in the presentation. Like go back to the document where you click this link. So this one right here.
It doesn't have the bit order, does it? It just says that there's a ROM here.
No, the little red markings.
The little red. Oh, you're right. Okay, it's got something there. Actually, I didn't notice that, to be honest. Oh no, it just says 0. No, it just says 01001.
Right, that's your first byte.
Oh, is it?
Yeah, that's the first byte. See, it skips. It's 2 blocks of 16 is each.
Wait, but didn't we just try that and that didn't work out?
No, we did each block. If you skip a block, that's what it is.
Oh, right. Skip a block. Right. Right. Okay. Sorry. And that's what I was getting at is, yes. And that's what I was getting at. There's two different ways. Let me get this back up. There's two different ways that I've seen the interleaving done. So you're right. I actually made a mistake when we were taking a look at this to some degree. So there's two different ways you can interleave this. One of them is where you put both bits of the say the least significant bit together, and the other one is where you have half of the least significant bit and half of it here. So yes, you are right. We need to try that other interleaving strategy. So I didn't notice that was in that doc. Otherwise, I probably would have probably wouldn't have looked at that.
Yeah, I missed it the first time. I actually saw it just before we went live.
Interesting. Okay, well, why don't you explain a little bit then, since we're skipping ahead bit there. What is the interleaving strategy then?
Right, so if you hold this, so if people see, it looks like there are groups of about 8 bits. Like you see, yes, the first group, then there's a second group, then there's third group. And there are 16 groups in total across that whole array, right? So what I believe we have found is the first 2 groups of bits actually total 256 bits. The second 2 groups of bits total 256 bits, and so on. So what's happening is the first bit of the first byte is the top left-hand position, and then the next bit next to it is the first bit of the second byte, third byte, fourth byte, and throughout those 256 is, you know, the first bit of every 256 bytes, right? The second group, it starts with the second bit of the first byte, and the third group of 2 is the third bit, and so on. So if you start here, and I think if you move your cursor to the first bit, right there, that's bit 1 of byte 1. Then you skip 2 blocks.
Okay.
That's the second bit of byte 1, and you skip 2 blocks. That's third bit of byte 1, and you'll notice you'll end up with 8 bits as you go along down that scheme.
Gotcha. Okay. And this is just based on matching up with the existing binary we have, right?
Yes.
Gotcha. Okay. Makes sense. And presumably, if we didn't have that binary, just a reminder, what we would do is we would run this assumption based on, I think I did this here, that this is maybe a common first instruction, and that we would pick that out from that as a guess, as kind of a heuristic. So even if we didn't have that binary, assuming this was a common start, we should be able to guess that. Okay, I think that sounds good. Maybe at this point then, if you have a good theory then about how the ROM is laid out, maybe we can switch to you and you can try to actually code that up into the framework so we can do the full extraction. Does that sound good?
Sure, yeah. So I can start presenting.
Sure. And maybe I can stop here.
Let's go here. And we can move. So I did some prep.
Let me also check real quick to see if there are any questions, because we just kind of made a big, let's see, LR substantial delay.
There are a couple of comments. Yeah.
Yeah. There are 8 blocks on ROM. Each block has 1 bit starting at bit 7 on the left. Sure. Okay, more of a comment than a question. All right. So yeah, do you want to talk a little bit? I think you set up some boilerplate code or something. You said to start.
Sure.
with.
Yes. So I set up the boilerplate code. I left the last important bit for you, and I'll let you know why.
Sure.
So if you want to add another architecture to the Zorum, and this is the Zorum tool, the link is in the description, and people can go look at the GitHub page. There's a directory of all the the classes for each of the architectures, right? And there are a whole bunch that exist already. I added this guy right here, the LR35902. If you, sorry.
Oh yeah, go for it. Yeah.
Okay. And before we actually dig into the LR52, a little bit of the boilerplate is there's a args file right here. So this is how you just import your architecture into the tool, a couple of import statements, a little entry into this dict, and you're good to go. That's pure boilerplate, not really a big issue there. So let's dig into the little architecture file right now. Let me open the LR52, and you see it's fairly simple. You know, a couple of kind of like description function, words, text width, invert, and then the OI2CR, which is a really important one. So the words function just returns the number of words in the whole ROM, and there are 256 of those.
Maybe to clarify words versus bytes, could you explain maybe what the difference could be there?
So in this case, the size of a word is 8 bits, which is a byte. So there are 256 bytes in this ROM, as far as I could figure out.
Yeah, that's true. But we have some
Mhm.
other examples in here where we have like 14-bit words and other weird stuff like that. And so for those, you have to define some more advanced metadata. I will say that by default, though, it calculates the number of words from the ROM size with txt.wh. So in this particular case, you also could have left that function out.
Right, and that's
Although,
actually what I figured out. So you know what? Let's go ahead and delete that. Let's simplify. Simple is better. The next actually important function I found was the text width height, which is txt.wh, and that gives you the number of rows and number of columns in your file, in your text file containing the bits, right? This is important. As you saw from as you showed from the text file, we have two groups of 8 bits going across, and then 16 groups, each being 8 bits long, going down, right? So it's 16 by 128.
maybe just a quick clarification there, though. The text file on Nevsky's, I don't know how to pronounce that, sorry, website is rotated 90 degrees, though, versus the microscope images that I have. And that's the reason why the width is 16 and the height is 128, as opposed to when we were just looking at it a second ago, the width was 128 and the height was 16. It's a little bit
Right.
arbitrary how you do it. I personally tended to prefer to put things more wide than tall, but either one works. They're functionally identical.
Right. Also, in your experience dealing with these different architectures and stuff, is there a reason why you have it as kind of like a matrix and not just a straight up like array? And then you just, point to different indexes in the array?
Oh, I mean, it's possible to do either. The point, though, is that it's a somewhat visual thing. And in my experience, it just tended to be easier to write the algorithm this way. But sure, either one would work. They're functionally equivalent.
Yeah, okay. Okay, very cool. The other function that I carried over from, copying one of the other files was invert. I'm not sure if this is needed or not.
Invert is required if in your text file you had a 0, but in the final binary it is a 1. I think in this case, though, there's actually one-to-one mapping, right?
Right. So I should set this to false because I don't know what the default.
The default is false, but yeah,
right.
I think it's fine to be explicit here.
Yeah, let's be explicit. So this is where all the magic happens, right? The OI2CR function. And as the tutorial that you wrote actually describes very well, is this takes the, given an offset and the mask bit, which is supposed to be in the binary file, you return the row, the column and row in your text file for that value, right?
That's right, yeah. Because we have to translate between the logical mapping, the binary, and the physical mapping, which is the microscope image.
Right.
And as you mentioned, I happen to choose to describe those as rows and columns in the physical layout because that made sense to me. And so that's how it's encoded here.
Sure. Could you just describe what offset and mask I is real quick?
Sure, yeah. So offset meaning so we have bytes here, so things are a little more straightforward. It's like, if you were to seek into a file, what is that offset? Like, oh, I am 3 bytes into the binary or 10 bytes into the binary. And for the mask I, that is the bit number, as opposed to, say, a bit mask can be basically encoded in 2 ways. let's say you wanted the most significant bit of a byte. You could say that's, hex 80, so that's the mask in kind of binary form, or you can just say that that's the integer, index of the bit, bit 7. And that's what mask I is. It's the integer mask, so bit 7. So most significant bit, for example, here would be 7 for mask I. Does that make sense?
Okay. And a little bit background on this tool. Does it just go from 0, 0 to, max bit and keep asking for it? Is that what it's doing here?
Internally, what it's doing, is it's basically indexing the map at startup. It's going to call this for every bit in your binary, and it's going to create a large dictionary that contains all those mappings.
Okay, very cool. So let's go ahead and get this coded up, right? So
sure.
We're gonna think of it this way, right? So we have in the text file, and
if you don't mind, do you mind? I actually had a command that I can give you that will rotate that text file to match the microscope image.
Oh, sure.
Would you mind doing it that way? Because I think that might make this a little bit more straightforward. And I think I might have sent that to you, but if not, I don't know what the easiest way to message. Maybe I can use this chat function. And that's kind of the command you want to use if you're able to get that.
Mm-hmm.
And you're gonna have to modify that slightly, for your, I sent it to you in the Zoom chat. I don't know if that you can see there.
I cannot.
Okay. Maybe you have to quickly exit full screen. Maybe it'll show up easier.
Oh, you know what? No, there is. Here's the chat. Okay. There
you got it?
Go.
Okay.
Yeah. Okay. So let's do this. Whoops. No file. Hello one. Okay. That's not what I want. I want text.
Oh, you might not need all those flips. I think you just need the rotate, right? Let's get rid of some of that.
And I don't need the invert either, right?
Yeah, I think get rid of those.
Okay.
And
so let's
wait, let's think about this real quick. I think you actually want rotate 270, because if you do rotate 90, I think it's going to be upside down. Why don't you open that up then? Yeah, and compare it versus the microscope images.
Okay, so this, did it lose groupings, a little white space?
It did, but the white space is more or less ignored by the tool.
Okay.
So
this is 001, 010.
Yeah, that looks right to me.
Does that look right?
Yeah.
Okay, I'll take your word for it.
Okay, and why don't you go back to your Python code then, and let's swap now the row and the column there.
Okay.
Oh, no, the text txt width height, because now it's wants those in the other order, right?
Yes.
Now, as a side note, if you do put it in upside down, it doesn't have a way to automatically detect that, so don't do that. Okay. Now you said you knew a bit.
It just discards all white space and
Yeah, and it's able to do a little bit of sanitary checking around width and height. So if you did flip it around 90 degrees, it'll complain. But if you put it upside down, it doesn't know the difference.
Okay.
And you'll just get a scrambled binary out.
Sounds good. So how are we going to do this? So offset is going to be.
Okay, well, we can think about this in terms of, where the bits are in the binary. I guess that's, to me, kind of a one way to think about it. And I think you said was it the most or the least significant bit was on the left of the microscope image?
The least significant bit.
Can we double check that?
The most significant bit. Yeah. So let's do this.
That?
Let's do this. It was what, hex 31, right?
I think that sounds right. Yeah, I can double check that. Yes, hex 31 is the first byte.
There you go. 1100. Yeah. So what do we see?
Well, careful though, because I think that was truncating that.
Yeah. So there are a couple of leading zeros. Yeah. And see, Google can do it too. Okay. So let's do this. So each mask I into 256, right? So like.
I'm sorry, I wasn't clear on the answer. Did we decide that the most significant bit is first then?
Yes, because it started with 0, 0, 0.
Yes. Okay, great. Just wanted to be really clear on that. Okay, sounds good.
And so I think we need to multiply mask I by 256.
Well, the way that I would think about it, yeah, is how many columns are you going to skip depending on what that value is?
Right. So, and I think that's right, right? So like, let's start writing this and you can correct me.
Sure, yeah.
So we got mask I into 256. I think that makes sense. 0 is 0. 1 is 256. 2 is whatever that number multiplied by 3 is.
And remember, I think you're thinking about it in terms of a 1D array. Remember, in this case, we have rows and columns. So if you have a value of 1, for example, you're actually going to overflow the number of columns, right?
And so we modulus this by is that correct? We're gonna.
Well, if you put a modulus there, you're going to cancel out the multiplication, right?
Okay, so this is why I said you're going to help me out, because you could we could sit here and watch me flop around with simple math for 3 hours.
Sure.
Or
well,
you could just give me the answer.
Maybe the first thing I would suggest. Well, I haven't actually done this before, just to be clear, for our viewers. So we're going to have to fumble a little bit through this, but I have done this for very similar chips. The first thing I think you need to do is you need to take the complement of mask I, because we said that the most significant bit is on the left, right?
Mm-hmm.
So okay, that means that, yeah, that generally, so we want to do, yep.
It's 7
exactly,
minus
yep.
mask I, okay.
Okay, then the next way I'm going to think about this is how many columns do we skip every time we change the bit?
16 it was 16, right?
16 sounds right
2
to me.
groups
So
of
what
8?
should you, yep, so what should we multiply that by?
16.
Yep, okay, so that's good. So now every time we skip a bit, we're going to go into the next group of 2 columns. And then from there, I think you said the address just linearly increased from left to right, right?
Yes, but it kept going down, right? So like,
right. So that's where we need the modulus then. So let's do plus offset.
Offset.
And how often does offset wrap around?
16, right? Because there are 16
exactly.
bytes
Yep.
each row.
So let's take modulo 16. Great. And I think our column selection is done at this point, honestly.
Mm-hmm.
So now we just need to select the row.
Okay.
All right.
So
how many bytes do we go through before we get to the next row?
16.
Yep. So let's just do that calculation.
So offset into 16? No, divide by 16.
Divide by 16, yep. Let me see if there are any questions. Nope. Okay, that looks about right to me. I would say save that and let's try running it and just see what happens. If you, it's also worth mentioning that this framework is going to check your map for consistency. So if you make some mistakes, like you return the same address twice or something like that, it should hopefully catch that. And then we can refine that if this looks like it, refine this if it doesn't look like it's working. Oh, didn't you have it in this directory? I thought you did a.
No, I had gone and rotated.
No, I see your lines right above, right? Oh, because you did the rotate and all. Oh, I see.
Yeah, no, that's fine. Let's do it as out.bin because I have the actual original one.
Sure, as long as you're going to keep this straight. Let's try not to overwrite that. Okay, give that a try and see what happens. Oh, you need to put the command name.
Oh, yes, sorry. Yeah. This is text to bin, right?
Yep.
No errors.
Okay. Well, that's a good start. Okay, so let's.
Yeah, I mean, hey, that's great for me. Like, you know.
Do you can you hex dump that file maybe, and we'll just see what it looks like?
Yeah, I can hex dump out.bin.
Sure. Wow.
Well,
that...
yeah, maybe. I
It's
think
close. It's close.
it's
It
close.
looks
It's close, but not bad. Okay, so you know what? Let me hex dump the actual gold set.
Sure. Now, I will add, though, that if we didn't have the golden, the way that I would actually recommend to do this is to disassemble this binary. That's what we would do in the, if you call this the real world, where we didn't have this reference. Do you have that disassembler ready? Can you run it on that file and we'll just see what it looks like?
You know what?
I can give you the command line if you need some help.
I actually, I set it up, but I forgot where.
Okay.
Okay.
In the meantime,
yeah,
I'm gonna paste you the command line. Okay.
Okay, let's do this. Let's do this. Let me try to find this. We can do it.
Okay.
Won't take too long. There we go, 64-bit. And you need DASM. There we go. There we go.
Great. And I've sent you the command line, so why don't you run that against it on the Zoom chat.
There we go. So let's do this. Control-C, close this baby.
Now, it's also worth mentioning on my to-do list is to write kind of an auto solver that takes some of the common patterns that I've seen, as well as some expected input, and tries some of these common permutations until it comes up with a result. But anyways.
There we go.
Maybe do a head. Let's do a head on that or something, yeah, so we can see just the.
Yeah, so let's do this. And this is the actual gold set.
Okay, sure.
Okay.
So it looks like it initializes the stack, and then it clears register A. And I don't know their assembly well enough, but I guess it loads a register and jumps or dereferences a value, maybe something like that. I don't know. Can you compare now to what does yours look like, just for reference? Maybe this is where somebody can shout out in the comments who's better at this assembly.
Okay, so here we go. This is this, right? So definitely the addresses are wrong.
Yeah, so that definitely stands out. So it loaded a weird value into stack pointer. And I would say that looks suspicious to me. Like maybe if they had loaded it at like 800 or something, I could have been like, oh, okay, that could be. But since that's 4711, that seems a little bit weird to me. I would probably flag that.
Here's a random question, right?
Oh,
if you were to take a file with a bunch of just random bits in there, would they actually disassemble to something?
It depends on the architecture. I mean, to do it right now, just feed in dev random.
Yeah.
No, I'm saying do it. Like, might as well, right?
Oh, you mean actually do it? Okay.
Yeah. Why not?
And you want to just check the comments? I think there were a couple of more comments there. So
let's see. Yeah, there's something about that. Set stack then clears VRAM. Oh, okay. VRAM is mapped there. Okay, good to know. Starting from 9F downward. Out of curiosity, why is it not the stack starting at FF, and why is it at FE instead? I think I'm curious about this.
No, it doesn't look like it's working.
Oh, what happened? Did it just get really annoyed?
No, it's not doing anything.
Okay, well, maybe we don't have to dwell on that if that's going to be hard to set.
Yeah, that's fine. Okay, so dev random. Oh shoot! No, no. Oh,
you have snow crashed.
Please
stand down.
I should have known better. I should have known better. Let me reset. Reset's a great command. Okay.
All right.
Anyways.
Okay. Technical difficulty. Stand by. All right. And now at this point, we have the bulk majority of it. I think it would be cool, though, if we could actually fully get it. It looks like you may have skipped bytes. Like, are the bytes there? They're just in the wrong order.
Yeah. So, like, you see there's an FE here.
Yeah. And so if you skip another 1, 2, 3.
Actually, there's no FF, which makes me feel. Oh, no. You know what? I think we're going down. Yeah. We're
Oh,
going
you're
down. So,
right.
right. So it's like if you
Oh,
read
okay.
down, we're doing the right thing.
Oh, okay. So it's pretty close. So you just have to rearrange it a little bit. So we basically, that's really funny. So 1, 2, 3, 4, 5,
That
6,
is
7,
actually quite
16.
funny.
Okay, pretty close. Well, so I think we could fix this, but I think people get the idea. We need to fix our math a little bit. Maybe we'll post-process this to get it fully committed, but I think that's kind of the bulk of what we had to go through. Do you kind
Yeah.
of agree with that?
No, I mean, yeah, this has been great. Like I've been curious about this, and I think I tried attempting this a while ago, but I kind of, it seemed too complicated, and I said, nah. But I think your tutorial that you put together helped a lot. Like, fundamentally, it's not that complicated what we're doing.
Yes.
So, you can, I think it just definitely takes a little bit of experience and trial and error, but
Yes, especially
it
since I think there's this kind of mixed physical hardware with software. I think if you're not familiar with that, it could take you a little bit to wrap your brain around that a bit.
mhm.
Yeah.
For sure. No, yeah, this was super interesting actually. And I think there's a lot more here, right? Like if people are interested, I think the first section of the pipeline, which is, you know, actually extracting the zeros and ones from the images in itself is a pretty interesting topic.
Hmm.
But yeah, I think today's episode actually is one of our longer ones, but people have been listening in, so thanks a lot for that. And if anyone has any more questions, for sure, please put in the chat or hit us up Twitter.
Yeah, and one other thing I'm going to add too is if you're interested in contributing to this project, one of my goals is to kind of aggregate a lot of the community knowledge into this framework. There are plenty of pre-existing algorithms like this out there that I would like integrated. So please hit me up if you're looking for a small project.
Yeah, for
Sounds good.
sure.
I
Oh,
think with that,
there's another comment, real
yeah.
quick, if you want to just address that before we leave.
Well, there's some things about the address map. I think it's more of a comment than a question. I don't know what else we could do with that.
Okay.
Okay.
But yeah, no, hey, thanks a lot for everyone who tuned in. And if you guys have any suggestions or comments on this episode or future episodes, definitely let us know.
All right. Until next time.
Thanks. Bye.
Bye-bye.